Hello everyone. Sorry I am absent. My daughter's sick, but hopefully this video will suffice. Also, I'm having virtual office hours this afternoon from like 3:20 to 4:20, so feel free to come to those. Okay, so I would just work on the warm-up like it's a normal lesson. Pause and come on back and I'll go through it. All right, I'll assume you paused. So let's look at this. So we have our velocity function. We're looking for total distance traveled from 0 to 5. So for total distance, we need to find our zeros. So if we set t squared minus 3t equal to 0, t times t minus 3 equals 0. So t equals 0 and t equals 3. So again, that's enough to tell you how to split it if you wish. I'm going to sketch a graph. And by split it, I mean split the integrals. So if we have a 0 at 0 and a 0 at 3, I'm going to test a point at 1 to see if the function is above or below the x-axis. So let's see. V of 1 would be 1 times 1 minus 3, which is 1 times negative 2, which is negative 2. As well make it a decent graph, I guess. And so it looks like our function is going to go down here, and then if that's true, since that's a 0, probably goes up right there, but let's see just to make sure. And I guess we're going to 5, so I might as well make another one. So let's try at like 4, so I'm checking around the 0, so right here. V of 4 would be 4 times 4 minus 3, which is 4, and so that's positive, so it looks like this is good. So we'll have our section from 0 to 3 that's a negative area, and from 3 to 5 that's positive. And so now if we do our two separate integrals of velocity, because again we're total distance, so we have to split the integrals, split the areas rather. So we have the integral from 0 to 3 of t squared minus 3t dt plus the integral from 3 to 5 t squared minus 3t dt. How do I know when to stop? Well, 0 to 5, right? So start at 0, end up at 5, and then the zeros tell us kind of the middle part. And then technically, this first integral from 0 to 3 will need to take the absolute value. But again, if you just take integrals over the right intervals, and one is negative, you just make it positive. So we'll get t cubed over 3 minus 3t squared over 2 from 0 to 3, which is 27 over 3, which is 9, but I'm going to leave it at 27 over 3, and then minus 27 over 2, and then minus, that'll just be 0, which I suppose is absolute value, right? Plus, this will be same integral, t cubed over 3, and this said no calculator, hopefully you use no calculator, 3t squared over 2 from 3 to 5. So for 5, we'd have 125 over 3 minus 75 over 2. And then for 3, kind of already did it, 27 over 3 minus 27 over 2. And I'm going to make everything into sixths so I can simplify. So this will be absolute value of 54 over 6. 27 times 3 is 81, so minus 81 over 6. The 0 I'm just going to get rid of, it makes no difference. And then this is, let's see, 250 over 6. Minus 75 times 3 is 225 over 6. This is 54 over 6 minus 81 over 6. Yay, fractions, mental math. So this is the absolute value of negative 27 over 6. Plus, in here we have, this is 25 over 6 minus a negative 27 over 6. So we have 27 over 6 plus 25 over 6 plus 27 over 6. The 27s are 54, so we end up with 79 over 6. But usually we'd want to say this like 13 and 1/6. So that's our total distance. Okay, so again, you can do it without a calculator. You just get to do lots of fractions. For displacement, again, displacement is where we don't really care where the zeros are. We don't care where the areas are positive, negative. We just add them up. So some of the areas will cancel, and that's totally okay. So for displacement, so for 2 here, we just want the overall integral from 0 to 5, so of t squared minus 3t. So t cubed over 3 minus 3t squared over 2 from 0 to 5. And we kind of already did this, but if we put the 5 in, we get 125 over 3, and then this is 75 over 2. If we put zeros in, we just get 0. Let's turn these into 6. So 250 over 6 minus 225 over 6. So we get 25 over 6, which is 4 1/6. So that's our displacement. And then lastly, for number 3, we started at 0, 8, and again 0 is time and 8 is your distance. And so final position is going to be 8 plus our displacement, so 8 plus 4 1/6. So final position of this particle would be 12 1/6. Okay, now let's go through and look at this packet. So I'll kind of tell you when you can pause and try on your own, things like that. But essentially what we're talking about is accumulation functions. And so we're kind of starting, and if you look, fundamental theorem of calculus, you can think of it as the integral of a derivative just gives you the function, and you do f of the top limit minus f of the bottom limit. And so this is another way to think. If you integrate the rate of change of a function from a to b, you'll get the amount of change. Just kind of interesting. And so what we end up with is this right here, if we rearrange and add f of a to both sides. So we have our, basically what this means is we have our initial amount, which would be our f of a, plus our accumulation, or how much is kind of added or accumulated, equals our final amount. And where this is coming from, so right here, this is a rate. A derivative is just a rate of change. And so if we think of how the integral of a rate is going to get our accumulation, that brings this together a little bit. So initial amount, accumulation is the integral of a rate. Sorry for that, circle that wasn't a circle. And that gives you your final amount. And so an example here, so you have a town, initial population is 5,500, so that'll go here. Population is changing at this rate, p prime of t people per year. Then if you integrate that rate from 0 to 10, that'll be the change over 10 years. So then you start with 5,500 and add the accumulation. And if it helps as well, when you're integrating that rate, technically we have the integral p prime of t is people per year. And then technically you're multiplying your dt is like your change in time, so that would be years. Years cancel, and so that's why your unit of the integral of a rate would just be people in this case. So pause the video, try to go through and figure out what your integrals would be for 1 through 4. If you're thinking like, I don't get it yet, that's totally okay. Don't pause the video at all. I'm going to show you anyway. So we're just writing a definite integral to determine the quantity. So in this case, you're typically going to have a starting amount, right? So for number one, you start with 30 gallons. And then the number of gallons, P of t, changes at this rate, gallons per day. We want to determine the amount of pollutant in the lake. That's fun. After 12 days. So we start with 30. Our accumulation is going to be the integral excuse me, of our rate, 1 minus 3e to the negative 0.3 root t dt. After 12 days, so 0 to 12. For number two, water is leaking. 10 minutes after the leak is discovered, there are 60 gallons of water in the tank. So we have 60, so we're going to have to start with 60. We're looking for how much water was in the tank when the leak was initially discovered. So actually before it started leaking, there was more water. So we're adding the amount that leaked out from 0 to 10 minutes, which is the integral of that rate, square root of t plus 1 dt. We have a pi. Sounds kind of like Newton's law of cooling, but it doesn't say that the rate of change is proportional or anything like that, so it's not Newton's law of cooling. So let's see, the pi cools at this rate. So 220 is the number we have. So again, we're going to have to start with 220 here because that's the only value we have. And then what's the expected temperature of the pi 15 minutes after it was removed from the oven? Okay, well, we know it was 220 after 10 minutes. So 220, the temperature is decreasing, it's cooling. So minus, well, if 220 was at 10 minutes, now we're looking for 10 to 15. Integral of that rate, 3 natural log of x squared. Okay, now we have a craft fair. People were entering at the rate of E of t, exiting at the rate L of t, people per hour for both. There were 200 people at the fair at the end of the first hour. How many people should be there 3 hours after it opened? Okay, what number do we have? Well, we have 200. Start with 200. We're adding because it's just an overall accumulation. If it ends up being negative, fine, but we don't have a definite decrease happening, unlike the cooling of the pi above. And so then we have an integral. There were 200 people. That was the end of the first hour, so we're going to start with 1. And we're looking for 3 hours as kind of our ending point. So we're accumulating the number of people from 1 to 3. And people were entering, so there's that rate. And then we have to subtract the accumulation of the people leaving, which was L of t dt. Okay, for this next one, so what do we have? We have a pipeline company.